Hey class, welcome back to lesson 11-3. Now we're still going to be talking about surface area today, but today instead of prisms and cylinders, we're going to be talking about pyramids and cones. Now before we begin, last time we talked about a prism as a box, right, with a top and a bottom and then an area around the sides. I want you to think of a pyramid as almost similar, except the bottom is still the whole kind of rectangle box part, or it might be a different shape. But then instead of a top, which is also a base, we're going up to a point. So what we're going to see today is how we kind of deal with the fact that, okay, instead of now having like a top and a bottom and all the sides around it, we have a bottom, and then the top is a point. And all the sides converge on that one little point. And you're going to see that a cone is actually pretty similar to that. So again, we're talking about pyramids and cones, and these are some shapes that, of course, we see in a lot of different places. Obviously, the pyramids were pyramids. They were square pyramids, which we're going to talk about what that means in a moment. And, of course, the cone part of an ice cream cone, let me turn my pointer around. The cone piece of the ice cream cone is, of course, a cone. So I also think you see cones in a couple other places. Notably, I don't know if anyone remembers the dunce cap from a lot of pop culture, but that is, of course, a cone as well. And, of course, traffic cones have a cone-ish shape. So a pyramid is an object where we have one base, right, so hopefully everyone can see this, and that can be any shape, and the other faces, well, it can be any polygon, any polygon, and the other faces, so these lateral faces are triangles, interestingly, always triangles, that meet at a common vertex, called the vertex of the pyramid. So hopefully everyone can see the point at the top, that's called the vertex. These lateral edges are the sides of the lateral faces, which are these triangle pieces. And then we have the base, and we have the base edges around the base. Now, we name a pyramid by the shape of its base. So remember when I said the pyramids are square pyramids? Well, that's because the base is a square. Here's where things get a little tricky. Pyramids have two quote-unquote heights. First of all, there's the real height, which we think of as being the distance between the ground, the base, and the vertex, the top. But then we also have the slant height, which if you've ever played, which one is it? I think Assassin's Creed Odyssey, where you have to climb up the Great Pyramid. This is the distance from the base, kind of as if you were climbing up a side of the pyramid. And that we're going to call the slant height. We're going to give it this funny cursive L as the symbol for that. So here we're kind of dealing with two heights. A real height, which is the altitude, the distance from the bottom to the top, and then the slant height, which we are going to need for our lateral area formula. So let's talk about those formulas. So lateral area here is going to be 1/2 times the perimeter of the base times the slant height. So perimeter of the base should be pretty easy to find. Slant height may be a little harder to find in some cases, but some of you might have noticed that the height and the distance to the side and the slant height form a right triangle, and that's actually going to be the tool that we use to find the slant height or the height if either is missing. Now when we get to the surface area of a regular pyramid, that's just going to be the lateral area plus the area of, in this case, one base. Notice there is not a second base. Last time the surface area formula that we used was LA plus 2 base because there was always a second base at the top. But in this case, the pyramid ends at a point. There's no area up here. Imagine trying to stand on the point at the top of the Great Pyramid. Obviously, you couldn't do it because it ends in a point, or at least it did at one time before all the expensive bits got stolen. So let's try our first example. This is a hexagonal pyramid. There's a lot of information going on here. I just want to point out a couple things. First of all, this here is the base edge, right? 6 inches between here and here. We could use that knowing that this is a hexagonal pyramid. The bottom's a hexagon, so we got 6, 6, 6, 6, 6, 6, and the perimeter is going to be 36, 6 times 6. They've also given us that this length in here is 3 root 3. Now that's always going to be the same from each side. That's the apothem. So the apothem is 3 root 3 over here, but is also 3 root 3 over here. And they also gave us the slant height. Notice the distance to climb up the pyramid would be 9 inches. So, first thing we're going to do is start using this formula for surface area, right? And that's going to be 1/2 times perimeter times slant height, plus the area of the base, which is going to be 1/2 AP. Remember, 1/2 times apothem times perimeter. That's our area of a regular polygon, which we learned last unit. In this case, we actually don't even need the height of the pyramid. We can just plug all the stuff in. So 1/2 times the perimeter times the slant height, plus 1/2 times the apothem, which they gave us, times the perimeter. And that gives us approximately 255.5 inches squared, which is about 256 inches squared. So we're done. Notice that's surface area. Surface area adds together lateral area plus the area of the base. And again, this is pretty strictly formulaic. They gave us the information that we needed, we plugged it in, and we found the answer. For number 2, we're now looking at the pyramid of Cestius, which is located in Rome, Italy. And using the dimensions in the figure, what is the lateral area of the pyramid of Cestius? Round to the nearest square meter. So I'm noticing that in this case we are given a height. Height is 36.4 meters. The base edge measures 30 meters. Now one thing they did not give us in this case is the slant height, so we're going to have to find that. And notice over here in the plan box it says, use the Pythagorean theorem to find the slant height. So watch carefully through this exercise so you can see how we're going to do that. First thing we're going to do, easy enough, is find the perimeter of the base. It is a square pyramid. Notice 1, 2, 3, 4 sides. Each side measures 30 meters. So we're going to come up with 120 as the perimeter of the base. That's easy enough. Next thing we have to do is find the slant height of the pyramid. So we know that 36.4 is the height, the true height, the altitude. 15 meters, notice that's half the side length. If we jump back for a second, you'll see this length here is of course going to be half of the whole side because it goes from the middle to the side. So that's why this measures 15 meters. And we want to know the slant height. So L squared equals this 15 squared plus 36.4 squared. And if we do all that out, we're taking the square root of 15 squared plus 36.4 squared, which gives us, okay, they didn't actually simplify that number down for us, but we'll see in a second. So now that we found that slant height, we should be able to find the lateral area. So lateral area, again, is going to equal 1/2 perimeter times slant height. Remember earlier we found the perimeter to be 120, and we found the slant height to be the root of 1,549.96. So we're plugging all that in, and we get roughly 2,362 meters squared. So again, in this case we found lateral area, not surface area, because they asked us for lateral area. So we're not including the area on the ground. This would only be the visible area, the stuff that's off the ground. And it comes out to about that. Again, this is kind of a plug in the numbers and get the answer kind of problem. The additional trick here, though, and refer back to this problem if you have trouble with this, is that we had to find the slant height first using the Pythagorean theorem before we could find that lateral area. Okay, so now we need to look at a cone. A cone is very similar to a pyramid. Notice it also tops in a point. The only difference is the bottom. Instead of being a polygon, a many-sided figure, this is a circle, which either has one side or infinite sides, depending on how you look at it. The lateral area of a cone is going to be 1/2 times circumference, or really the same as perimeter, times the slant height, which in this case is going to simplify down to pi r L. So pi times the radius times the slant height. The surface area, on the other hand, is going to be the sum of the lateral area, so all this stuff up here, plus the area of the base. So again, just like a pyramid, surface area equals lateral area plus base area. So let's get into this. This is the surface area of the cone in terms of pi. So remember, we are going to leave pi in our answer. Radius here is 15 centimeters. Slant height is 25 centimeters. That should give us all that we need for this problem. We're using the formula surface area equals lateral area plus base. We plug in pi RL, that should give us lateral area, and pi r squared, that should give us the area of the base. So now we do some multiplying. We get pi times 15 times 25 plus pi times 15 squared. Notice we're plugging in 15 for the radius, 25 for the slant height. And we get 375 pi plus 225 pi, which if I'm correct is 600 pi. Nice. So the surface area of the cone is going to be 600 pi centimeters squared. And remember, that's the whole surface area, including the top part and the base. So that's all for this lesson. Homework 88 is going to be due for next time. So what I want you to do are page 1629, number 15 and 17, page 1630, number 20. Feel free to discuss those on the Slack as you like. And I'd also like, before next time, for you guys to review the 11-4 slides, which is what we're going to be going over next class. Thanks and good luck.